right, so welcome to our bonus lesson of Unit 2 for AP Stats. This is not always tested on the AP exam, so it's for our general knowledge. It may or may not show up, but either way, who's going to deny wanting to learn more? So let's talk about transforming nonlinear data. Now, the first few lessons were all devoted to linear data and using lines as predictive models. But not everything is going to resemble a linear pattern. Right? So our world operates in more than just linear functions. And so thinking back to your Algebra 2 days, we can use different functions to model information about real world situations in order to what we call linearize the data. Meaning once we transform it, it should appear a little bit more linear. And this is just going back to our functions of logs, natural logs, exponential functions, because we all know our world is not a very linear place. So here are 3 examples. Again, recognizing them is helpful, but if you don't recall the vocabulary, all we're worrying about here is that this is non-linear data in our scatter plots, and we're trying to linearize that data. So the first type of transform model is called an exponential model, where you take the log of the predicted response variable, and you can see that we still have the a plus bx. And so we've kind of got this exponential curve going on here, and once we transform the data, we get a bit of a more of a straight line here. Or you can have a logarithmic approach where you see that maybe you have this slow, okay, I have to go backwards because I'm mirrored, but you see you have this slow gradual approach. So you take the log of the explanatory variable. You can still see there's slight curvature here, but it's a lot better than this extreme curvature. And then lastly, we have the power model, which is where you take the log of the predicted response and the log of the explanatory variable. And you can see that that's going to do a pretty good job of linearizing that. So basically, EL, LL, LLL. I don't have a cute acronym for this. So exponential, you start with the log. Logarithmic, you end with the log. And there is power in having both. So you take the logs of both variables there. I got no cute acronym. I'm so sorry. But perhaps your data doesn't look like one of those transformations. So if there's another evident pattern in the residual plot or even in the scatter plot, try more basic parent functions such as a quadratic function, absolute value, an exponential, natural log, or even a radical or root function. And after we transform the data, again, we are looking for 2 key components, a relatively linear pattern in the scatter plot and then no evident pattern in that residual plot. And here are just some examples of some inverse relationships. Remember, these functions undo one another. If I were to substitute in the original function into the inverse or vice versa, I should end up with just an x. But enough algebra for today. We're just going to look at some examples here. So 2 variables, x and y, were measured for a random sample of 25 subjects, and 2 separate regression models were fit to the data. Least squares estimation of the parameters yielded the following equation, and residual plots for 2 separate models. So here we can see in model A, a power model, we see that it's a residual plot, so we want our residuals to be random, we want them to rebel. If I can see an indicative pattern, this kind of looks a little curvy, a little quadratic-esque. This is probably an indicator that there's still some underlying pattern in my data, so maybe a power model is not going to be the most beneficial. Whereas here, if I only take the log of the response variable, and not the log of the explanatory variable, I can see there's a bit of a more random scatter. So in this case, maybe an exponential model might be more beneficial than a power model. So which model is a better fit for the data? What evidence would suggest this? All right, so we need to answer the question, model A or model B? Well, model B would be a better fit for the data. All right, so model B, and I don't even know my response variable, so it's going to be hard to give context here. So we'll just go with what we have. So ACE, we answered the question. There's not really a lot of context, so let's explain. Model B would be a better fit for the data since there appears to be no evident pattern in the residual plot as compared to a curved pattern in the residual plot of model A. And again, I don't have any context here, so I can't elaborate further on this, but that would get us full credit here. Which model is better? Well, probably model B here because the errors are more random, so that's a good sign that a linear model would be appropriate. So I just have 2 example questions for you. This lesson's pretty quick. Here is a predictive question using a power model here. only one natural log. We're not taking the natural log of the natural log, so don't worry there. So here's a predictive question, and then also here is another question from 2004, the FRQs there. So go ahead and pause the video, try making some predictions, try describing your scatter and residual plots, and we will come back whole group to review as we typically do. All right, so pause the video, use your notes, and best of luck. All right, so hopefully not too complicated. Hopefully remember that the inverse of a natural log function is the exponential function, specifically base e, about 2.71. So here are just two examples. One was a direct substitution problem, so we should get that the height should be about 92.95 feet, very tall tree. Or going backwards, if we wanted to find that predicted value, then we should get that the circumference should be about 348.63 inches. I'm going to have to check my work on this red one, because now that I'm reading it, I'm wondering if it's saying the natural log of h hat should be 105, or the natural log, or the natural log of h hat is 105, or it's natural log of 105. Because now that I'm thinking about it, 348 inches in feet, 29 foot circumference, it's totally possible. I am not well versed in trees, so we'll keep caution of that. But here, we had the Earth's moon has many impact craters that were created when the inner solar system was subjected to heavy bombardment of small celestial bodies. We looked at 11 impact craters on the moon to determine if there was any relationship between the age of the craters and the impact rate. So looking at the scatter plot here, I said something along the lines of there appears to be a strong, negative, and nonlinear relationship between impact rate and age, and I didn't notice any particular unusual points since this does follow a very nice nonlinear curve here. Now, we go ahead and transform using some type of power model, because notice that the natural log happens on both the explanatory variable and the response variable. But even after this transformation, I can see that in my residual plot, there is an evident pattern. So a linear model would not be appropriate for the transform variable since there is a curve pattern in the residual plot. And we want our errors to be completely random. We don't want there to be any evident pattern when we're looking at the errors, because that is a bad thing. But nonetheless, that is actually going to conclude our study here of linear regression and a very fun bonus lesson on nonlinear data. So you have everything you need now to be successful for that 5 to 7% of the AP Stats exam on bivariate data. So stay tuned as we talk about Unit 3, collecting data.